Before we finish our discussion of drawing Lewis dot structures for molecular compounds, I'd like to do two final examples with you, one involving polyatomic ions and one involving molecules with more than one central atom. So let's look at our polyatomic ion situation first. And the ion that I am using for an illustration is the nitrate ion. Its formula NO3 with a -1 charge being carried by the entire ion, called the nitrate ion. You need to begin working on memorizing the names and formulas of ions found on the table of ions and their charges located at the end of your lab manual. So let's see how we tackle this example. We see that there is one nitrogen atom and 3 oxygen atoms. So we know to begin this structure by placing nitrogen central, since there is only one of it, and placing the 3 oxygens around the nitrogen atom in the terminal position. So we have a bonding sketch, step 1. Step 2, we need to determine the total number of valence electrons in this ion, and the periodic table is going to guide us through that. Oxygen is in family 6A. It has 6 valence electrons. There are 3 oxygen atoms present. 6 times 3, 18 valence electrons coming from the oxygen. Nitrogen is in family 5A. There is 1 nitrogen atom, so 5 valence electrons. And here comes the twist. Because this is a polyatomic ion, we have to take into consideration that there is 1 extra electron being carried by this species because of its -1 charge. So we have to include that in our total. If we add up 8 and 5 and 1, we get 24 valence electrons that should be showing in our picture. So coming to the bonding sketch, we begin by bonding all atoms together using a single covalent bond. Always start using single covalent bonds. We're then going to complete the octet of the surrounding or terminal atoms first. So I am going to place 6 extra electrons on each of the oxygen atoms to give each one of them their required octet. Now we're going to stop and see where we're at. How many valence electrons have we used up? Well, there's 8 valence electrons here, 2, 4, 6, 8, another 8 here, and another 8 here. So that gives us a total of 24 valence electrons showing in this picture. And that's all of the electrons that we have to work with. So is this the correct structure for the nitrate ion? I hope that as you look at this, that it's immediately clear to you that it can't be the correct structure because nitrogen does not have an octet. It only has 2, 4, 6 electrons. It is not satisfying the octet rule, so this is not the correct structure for the nitrate ion. Well, what do we do in a situation where the central atom does not have an octet? Step 4 of the process says that we can use unshared pairs of electrons on the surrounding atoms to form additional bonds. Nitrogen needs 1 more bonding valence pair. The question is, does this oxygen atom, far right, serve as the donor of the electron pair, or does this oxygen atom serve as the donor, or does this far left oxygen atom serve as the donor? Which one should we use? And it's obvious that any one of the oxygen atoms would be equally good candidates. So in this situation, we recognize that we're looking at an example of resonance. Resonance exists when you can draw more than one valid Lewis dot structure for the species. So this first structure that I'm drawing shows the far right oxygen atom serving as the donor of the extra electrons to form a double bond with nitrogen. So I'm only going to place 4 valence electrons around the oxygen because it's engaged in a double bond with nitrogen. The remaining oxygen atoms are singularly bonded, so I am going to give them 6 valence electrons. And now I'm going to stop and look at my picture. Does every atom have an octet? And as I look, I see nitrogen has its octet, double bond here, 2, 4, 6, 8, and all of the oxygen atoms likewise are obeying the octet rule as well. So every atom has an octet, and as I look at the count, I see that it is adding up to the correct total number of valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. So it's satisfying the criteria that make it a valid structure. But maybe this bottom oxygen atom can serve as the donor instead, so I can draw a second resonance structure for the nitrate ion where the double bond is forming with the oxygen that is terminal, giving it 4 electrons now to complete its octet, and the remaining oxygens get 6 electrons because they're singularly bonded. I look at a structure here that's different from the one I drew above, but with quite a bit of similarity to it as well. I see that nitrogen has its octet, all of the oxygens have their required octet, and the picture is showing 24 valence electrons, which is the correct total number. And I think we all see what the last resonance structure would be, where the double bond forms between the nitrogen and the far left oxygen atom. So quickly putting this in place. And again, I see that the octet rule is satisfied for all of the atoms, and it is showing the correct number of valence electrons. So illustrating the octet rule that is being met. One last thing before we leave this, and this is an easily omitted little detail. The nitrate ion is not a neutral molecule, it's a charged ion. And we need to indicate that in our dot structure by bracketing the species and putting that -1 charge to indicate that it is not a neutral atom, it is a charged ion. So we are illustrating an example of resonance structures where you have more than one valid Lewis structure possible for a species. So more than one valid Lewis structure is possible for the nitrate ion. We can draw 3 of them. Whenever you encounter resonance, that's an indication that something deeper and more complex is going on with the bonding that cannot be adequately captured by the Lewis structures. So as you move on into more advanced chemistry classes, you'll get greater insight into what's happening when you observe that resonance is possible. Let's take a look at our last example that I want to touch base with you on and talk about. And this involves molecules that have more than one central atom. So the example that I'm giving to talk about is ethene. And ethene falls in the category of organic compounds. And organic compounds are compounds where carbon is the principal element. Carbon is a principal element. What's wonderful about carbon is that it has the ability to form stable covalent bonds with itself, unlike any other element on the periodic table. Therefore, we have a whole branch of chemistry devoted to carbon-containing compounds called organic chemistry. Looking at this structure for ethene, we see that ethene has 2 carbon atoms present. That's our clue that it is an organic compound. So as I just said, carbon forms stable covalent bonds with itself better than any other element on the periodic table. And I'm going to start my bonding sketch by drawing the 2 carbon atoms bonded together using a single covalent bond. I have 4 hydrogen atoms to distribute, and symmetry suggests that I give each one of the carbon atoms 2 hydrogens, so it's evenly balanced. So looking at this picture, how many total valence electrons does it have? 2, 4, 6, 8, 10 total valence electrons. But how many should it have? So we have to stop and count the total number of valence electrons so that we can proceed further. Carbon is in family 4A. It has 4 valence electrons and there are 2 carbon atoms, so that gives us 8. Each hydrogen has only 1 valence electron. There are 4 of them. 8 plus 4 gives us a total of 12 valence electrons that our drawing needs to account for. But as we just observed, this drawing is only accounting for 10, not 12. So we have 2 extra electrons to place, and it's clear that they need to be placed on the carbon atoms because they do not have an octet. So let's just stop and see where we are right now. Hydrogen, each hydrogen has a total of 2 valence electrons, and that is exactly what hydrogen is interested in because hydrogen and helium follow the duet rule, not the octet rule. They are found in period 1, which can only hold a total of 2 valence electrons in that first energy level that period 1 elements represent. But carbon will definitely need to have an octet, and as I look at the drawing, I see that each carbon atom has 7 electrons, not 8. So what are we going to do? Well, a very reasonable solution is to have these 2 unpaired electrons swing down and become a shared electron pair and form a double bond between the 2 carbon atoms by having this additional set of electrons pair up. And now we have a Lewis structure that looks like this. So what is our check before we sign off? Is this structure showing the correct total number of valence electrons? Looking at it, I see 2, 4, 6, 8, 10, 12 valence electrons. That's the right number. And I see that each carbon atom has an octet, and that's what carbon wants, while all 4 hydrogens are showing the duet that hydrogen is interested in having. So this is a valid structure for the ethene molecule.